Hello, everyone. Welcome. So, I'm going to get started immediately, and I will take you back a few years, well, a couple of years ago in my own career when I was still young. And I was basically building a system for a customer. They were building an online offering. They had a bunch of physical stores. They were pretty successful, and they were like, we want an online offering so that we can expand that. So we started to build the system, and yeah, after a couple of years of working on this, the system looked somewhat like this. A monolith. Now, this is actually a monument called the Monolith. It's in Oslo, Norway, and it depicts 121 people. It's built from a single piece, one ginormous rock. So it's actually pretty magnificent, I would say. And the reason that I chose specifically this example is because over the last few years, the monolithic architectures have gotten a really bad reputation. But actually, there's a bunch of advantages that come with that type of application structure because it's a lot simpler, right? From the developer experience type of point of view, it's super simple, usually managed in a single solution, maybe a couple. It's easy to test, it's easy to debug, and also from a deployment perspective, you don't have to think about multiple versions and which components are compatible with which components and all that. So versioning is something that you don't need to care about. So it's actually quite an easy architecture, especially when you're starting to build an application. You don't fully understand your business requirements yet, and you don't even really know what you're building just yet. Now, this type of architecture was actually quite successful for us for quite some time. But then the application, the system got really successful, lots of users, lots of sales, and that's when it did start to show some cracks. And those cracks basically manifested as failing requests. Sometimes we would lose requests, which wasn't great. We also during high peak, saw that there was a significant strain on the single database that was supporting this entire system. And sometimes the system would also just crash entirely, so that was not great. So given that load that we were experiencing, we were like, okay, how can we evolve our system? How can we change our architecture to basically be able to deal with that increased load that we're seeing? And we quickly came to the conclusion that messaging was going to save us. It's going to be awesome. We're just going to change this architecture. We're going to move to a message-based type of system. We'll have multiple components interacting together. We'll have all of that load stored on our broker, and that way we'll be able to manage that a lot better. And that's not the only thing, right? There are so many benefits when it comes to using messaging in a system, because it's going to lead to better performance, right? Because we can manage that a lot better. We can scale those components that need it. And we will also see increased resilience, because if something fails, our message is always safely stored on the broker. It's also going to be a lot easier to decouple this application. And through that decoupling, we can also scale our system a lot more granularly, basically the services that need it. And those that don't, we can just leave them as is. So it's all just going to be great. But we did ignore all of the challenges that we were also introducing by moving to this message-based system. And that's why we started to bump into quite a few walls. Now, the first problem that we found is that actually our system became slower. What? It was supposed to be faster, right? We also saw that the UI became inconsistent. There were glitches, and sometimes data was just outdated, and our users got confused, like, what happened to my order? And lots of support cases, so that was tricky. We also encountered duplicate messages. And then the thing is that we started to see failures in the system because we've already processed that. What are you trying to create this order again? It's already there. We also found that sometimes messages were being processed out of order, and that didn't only lead to failures. No, it would actually lead to side effects and just things that were plain wrong. And we didn't really account for that in the beginning. And finally, when we were troubleshooting all these types of problems, we also found that it was just so much harder to troubleshoot altogether, because we had messages flowing in the systems, and this is being published there, and that's being sent over there, and everything is coming in at different times, and it was like, what is happening? So very overwhelming. And we basically tried to battle these problems as we ran into them and fix them as well as we could with the knowledge that we had at the time. But after doing that firefighting play for a couple of months, we realized that, our once beautiful monolithic application looked a lot more like this, a distributed ball of mud. So we had to sort of take a step back and admit to ourselves that we had actually made things significantly worse, right? So my name is Laila Bougria. I'm a software engineer and solution architect. I work for a company called Particular Software, where we build in Service Bus, which is a messaging middleware framework. Clearly, message-based systems are what we do, but long before I worked for Particular, I was out in the field building these types of systems, running into many of these problems and trying to figure things out as I went. So that's why I'm basically here to sort of share those findings with you so that you don't necessarily have to repeat my mistakes unless you really want to. But yeah. And another thing that I want to say is that a lot of the problems that I will be talking about are not necessarily exclusive to message-based systems alone. They could also be applicable to distributed systems, even though you're not using queuing even in your system. So let's zoom into all of these problems that I've sort of laid out. The first one is that the system became slower. Now, in order to understand why did it become slower, messaging promised us more speed, right? We also need to understand how did this system work in the beginning. And one of the things that we need to look at specifically is the communication patterns that were used. And the thing is that one of the main communication patterns that we used was request-response. And this is basically a synchronous type of communication where the sender and the receiver are coupled together. They're aware of each other. So what happens is the sender is going to send a message that is going to be immediately executed by the receiver, who's then immediately going to send that response back. Now, whether that's in your current systems, whether you're using gRPC or HTTP or even WCF, that's the underlying pattern, right? Request response. And we had been using this pattern for years. We were comfortable with it, so it was only natural for us to start doing this over messaging. And that's where the slowdown becomes apparent, because where synchronous request response looks something like this, where there's a direct connection between the producer and the consumer, when you start to do that over messaging, that's really the reality, right? Because your producer is going to send a message that's going to go onto the request queue, and when that consumer is available, has time, it will pick up that message and process that out of band. That's happening on a different thread. That initial thread on which you sent the message, that's long gone. It could even be, at another point in time even. Now, when that message has been processed, then the response goes into another message that's put onto the response queue. And again, the producer, when they're up, when they're available, and they have time, they will then process that. And one of the things that I like to stress that it's important that when you sort of evolve to this message-based type of systems, event-driven systems, that it's important to understand that we're making the communication asynchronous. And I like to use sort of silly analogies. So I'll take you back to my teenage years when I got my first cell phone. No, actually, my mom got her first cell phone. I already had a cell phone back then because that was the deal, right? Now, the thing is that one of the first functions that she learned how to use was making a phone call. And boy, did she know how to use this function, because she would call me all the time, like all the time. And yeah, the reality is that I wouldn't always pick up. Sometimes I was in class, sometimes I was with friends, and sometimes I just didn't want to. Sorry, Mom. So the thing is that this had a big impact on her, right? She would get super worried, like, oh my God, is she okay? What is going on? And sometimes it would completely hijack her day. She wouldn't be able to do like whatever she had planned because she was so worried. So it had a direct impact on her. So at some point I came home and I was like, Mom, let me tell you about text messages. And I was like, whenever you need me urgently, of course, give me a call. But if you're just, want to check in, see how I am, then please just text me and be a little patient and I'll get to it when I get out of class or whatever. And yeah, my point with this sort of analogy is to underline that even in an event-driven system, even in a message-based system, not all type of communication is suited to be asynchronous. If you need something directly, if there's somebody waiting on the other end to be able to continue their flow, then still use synchronous communication. So let's consider which communication patterns are available to us when we're building message-based systems. And there's actually 3 to choose from. We have one-way communication, request response, and the publish-subscribe pattern. I'm going to continue with my silly analogies. And this time, we're sort of, I'll walk you through family dinner at home, right? So my husband is actually the one who cooks on a daily basis because he really enjoys doing that, and I just take care of the kids or whatever, the household in the meantime. So at some point in the evening, he'll look at me and he'll send me a message and say, honey, I'm going to start making dinner. Now, that message is directly for me, right? It's specifically for me. He wants me to be aware that he's going to start doing that. He does not expect a response from me, right? I can continue doing whatever I want, whether I was, with the kids or just, sitting around, it doesn't really matter. He just wanted me to be aware. At some point, dinner will be close to ready, and I'll see sort of his face pop out of the kitchen, and he'll be like, dinner in 5, right? At that point, it's request response. He does expect me to respond in some way. What does that mean? I need to get up, take the kids with me to the kitchen, make sure that the table is set, for example, and things like that. Still asynchronous. It's not that he's standing like that, like, come on, come over. As long as I respond within an acceptable time frame, then, I can just get to it. Now, if it was a good day and the kids ate well, then at some point my husband and I will look at each other and we'll say, you know what, the kids deserve some ice cream. And then we'll publish an event saying that there's ice cream available. Now, why are we using publish subscribe for that? Because the kids are old enough. We're not dependent on an answer or on a response from them, right? They can get up, they're old enough, they know where the fridge is, they can just walk over and grab whatever ice cream that they like and then continue. But I promise you that they are subscribed to the ice cream available event. Now, in order to start applying these patterns to a system that used to be sort of monolithic, we still need to engage in one of the most important parts that can help us make us successful at building these types of systems, and that is decoupling. Because I know when you start reading about messaging, one of the things that always comes up is that it makes decoupling so much easier. And that is true, but it's still an activity that you need to engage in. It's not going to just magically happen because you're using a queue somewhere, right? So let's consider a few techniques that can basically help us decouple a system. Now, I'm going to use our trusted order process, right? Because we all know that and can reason about it. So if we would sit together with business experts and they're telling us, like, this is how the system works, we could quickly come up with something like this, right? Now, the thing is that when we have those conversations with these business experts and they tell us about something like that, they're telling it in a specific order. And the thing is that it's only human to immediately assume that order in our heads as well. So one of the things that I try to do consciously is immediately remove any ordering, any arrows from my mind, and start basing those answers based on questions. So one of the things that we could ask ourselves is, which steps of this process naturally happen at a different point in time? And we could say, well, clearly packaging and shipping, because that requires some type of human intervention, and stuff has to put in a box. We need to call the third-party provider, whatever it is, right? But it could also be, for example, ordering more stock, because we're just used to doing that on a Friday, and there's some calls with basically the people that deliver us those products, maybe. But another thing that we also want to do is look at what are the prerequisites for each individual step, right? For example, we want to adjust the stock immediately after we package the order. We don't want to wait until we've actually built that order. There's absolutely no need for that. Or, for example, verifying the customer status, that may be something that we want to do when the entire order has been fulfilled, so it's dependent on a couple of steps. Could be, right? These are the things that we need to figure out. Another thing to ask ourselves is to look out for those technical prerequisites that we tell ourselves are there. For example, is it really required that we store the order before we charge the credit card? Not really. If we would just assign the order ID up front, then it doesn't really matter what we do first, right? But the thing is that at least I've been using relational databases for years, and we've been taught like the main entity has to be there first so we can lay those foreign keys, and that sort of gets us stuck in this thinking. So there's a little bit of unlearning that needs to happen there as well. The next step that I usually take is to try to differentiate between if something fails, what needs to be rolled back and what can be compensated. So for example, if I'm able to store the order, but I'm unable to charge the credit card because it bounced or whatever, does that mean that I need to delete the order from the database? Probably not, right? We can send the customer an email and tell them to update their payment information, and we want to keep that order in our database. If I'm able to charge the credit card, but I don't have enough stock to actually package that order, then what? Do I need to refund immediately? Not necessarily, right? We could maybe back order those products for them or wait a couple of times until that comes in and then maybe later, at a later point, refund. So really the point is to identify those bits and pieces that can succeed on their own and to isolate those from each other. Now, another thing that is really important to also keep in mind is how the data is being stored. Because for example, I've been talking about an order for a while, and I'm sure that everyone understood exactly what I'm talking about. It's a concept that we can basically, share and think about and reason about. But if you start thinking in terms of a system, in terms of the data that is being stored, it actually means a bunch of different things. Because in the context of a specific sale, we care about the order reference, we want to know who ordered it and when that was done. But in the context of a payment, we'll care about the payment method, the total order amount, and whether they got a gift card or a voucher, for example. In terms of packaging, we'll care about how many items, how large they are, how heavy they are, and things like that. For shipping, we'll care about how many packages are there. Are there any fragile items, for example? And did they choose express delivery? But in terms of the invoice, we only care about, do they want a physical invoice or a digital one? And are they VAT exempt? And the thing is that because we can reason about an order, that's the reason that you'll find so many systems where there's an order table. But it's important to sort of step away from that entity-based thinking and to start thinking about which attributes of an order are actually coupled together. So what we basically want to do is find the right service boundaries, and those things are going to help us do that. One of the things we want to do is identify what behavior is likely to change, because that's then something that we'll want to isolate, because that tends to change. What data changes together, that's also really important to sort of see what service boundaries would be useful, because some of that data will never change, and some of that data may regularly change. If you think, for example, about a product, right, that has a price. If I change that price, is that going to impact the product name? Probably not. But if I change the product name, is that going to impact the product image? Well, maybe if you're doing a rebranding, right? So it's important to think about those attributes independent of each other and to try to think like, what is basically coupled together? What data and behavior depend on each other? For example, let's say that, in your system, based on the customer status, gold, silver, bronze, whatever it is, we have completely different pricing, not discounts being applied, no, completely different prices per product. Well, then those are coupled together, and we should keep them together as well, because they're going to change together. And then you have data and behavioral changes there. Also ask yourself, what data pertains to the same transactional boundary? If you need high consistency between this attribute and that attribute, then they should be together. Because if you pull them apart into different services, there's no way that you can achieve that high consistency. And one of the things that you can do is practice finding anti-requirements, where basically you look at those attributes of a product, of an order, whatever you're working with, and ask yourselves, for each attribute, to what is that connected? Sometimes that will lead to some silly questions, but if someone looks at you funny and says, like, what kind of a question is that? Then you've probably found something that is completely unrelated, and that's a good thing. Now, if we want to practice finding anti-requirements, I just said that we have to ask questions, right? If we're going to be asking questions, then we need to do this with the business. It's not something that we just, as engineers, can do on our own. We need to engage in those conversations with them. A technique like event storming can be really great to apply so that we can understand how these things connect together, even from people, and hearing that from people who have completely different responsibilities, right? The underlying goal that we have is to uncover any false assumptions, because it's a human trait to make assumptions, right? Especially because of our previous experiences. Maybe we've already worked in retail before, and that's how we did it in that system. But you're in a new business, and maybe they treat things differently. So you need to try to find which assumptions am I making, are they false, and break them apart. So yeah, keep asking questions, be super annoying. It's really, really helpful. And yeah, you have to also factor in that this is going to take some time. You're just not going to figure this out on a single meeting. It's not something that you can figure out that quickly. It takes a while to sort of deepen that understanding and continue digging deeper. Now, we did this for quite a while, and then we ended up somewhere here. We identified 7 subdomains, and although this may look a lot more complex, it's actually a way better representation of what the system actually needed for that specific business scenario. And now that we can also have those boundaries separately, we can also make different decisions for each individual service boundary. And we can then sort of circle back to our communication patterns and messaging, one-way communication, request, reply, and publish, subscribe, and ask ourselves, okay, now that we have all those services, how are we going to communicate between them? And which pattern are we going to use in which specific scenario? Now, the publish, subscribe pattern is even one of my favorites, and it's a very popular one. Why? Because it has the highest amount of decoupling. Right? Why? Because we're inversing the relationship. It's not someone else who's telling you something, but you just opt into whatever you care about from your services perspective. But as with every good thing in this industry, we also sometimes misuse it. And that leads me to the passive-aggressive publisher. And I'm going to circle back to family dinner for this one, because my husband was kind enough to cook, I will usually clean up the kitchen. But there are some of those days that I walk into the kitchen and it's like, what happened? It's like a bomb went off. And I'm thinking, like, did he use every pot and pan that we have? Now, at that point, I could choose to publish an event and state the kitchen is messy. And that's a valid event, right? It's a state that the system has arrived to, and it's a fact, right? The kitchen is just very messy. But the thing is that there are underlying hidden assumptions there, because first, I'm expecting that my husband is listening to me. And second, I'm expecting that he's actually going to get up and help me clean up the mess, right? Now, I think we can all agree that that type of communication, not very good for your relationship. Well, guess what? It's not really good for your systems either. Because what you're really doing is you're hiding the coupling away. You have coupling. Sometimes you need coupling, otherwise we wouldn't have systems. But when you need it, make it explicit. So publish, subscribe is not really a good fit when you expect something specific to be done and you need control over that. Then, use command-driven type of communication. If you need a response with data in order to continue your own responsibility, publish, subscribe is not the best way to go. And finally, if you need control over who receives the event, also not a good fit, because a publisher should be completely unaware of any subscribers. You shouldn't even care if there are any, from your services perspective. By the way, this term was initially, I read about it, I think on Clemens Vaster's blog, and he called it passive-aggressive events. I kind of changed it to publisher because I feel that that's the party that's making the decision about being passive-aggressive, right? Okay, so to recap this first part, this first problem, it's important that we decouple our components by finding the right service boundaries. Otherwise, we can't really be successful at building these types of message-based systems. We want to localize changing behavior and data dependencies and help and use those as mechanisms to find the right service boundaries. And we also want to pinpoint the transactional boundaries of our services, because that will tell us a lot about whether we got them right or wrong. And then finally, based on that, we can choose the right communication patterns to help us sort of communicate across multiple components. And that brings me to the next problem. The UI is inconsistent. The thing is that as we sort of evolve from this synchronous type of communication to asynchronous type of communication, we are basically accepting the fact that things are going to happen, but at some point in time, and we don't really know when anymore because we've let go of that. And sometimes that can cause some glitches, right? If we don't change how our application works in the communication with our user, that's going to lead to those, data that looks outdated and glitches and things like that. But there are techniques that we can basically apply to mitigate that. And the first one may be obvious, but it takes a lot of work. We basically want to adjust our language, right? Because if we tell our user, well, thank you, we've successfully processed your order, then what are they going to expect? A successfully processed order. But if you tell them, well, thank you very much, we got your order, give us a minute and we'll get to it as soon as we can, then we're setting completely different expectations. But the thing is that if you're coming from an application that was purely synchronous before, moving to this is actually quite a lot of effort. So there's also another technique that we could apply, and that's basically creating the illusion of progress. Because that's the thing, right? Users do something in a system and they expect progress. They did something, they want to see the result of that. But the thing is that we can't give them that, or we don't know exactly when we can give them that. But if we can ensure message delivery, and we know, okay, this specific message has been safely stored on the broker, then we have a guarantee that it will be done at some point, right? So one of the things that I like to think is that we can then, use some creative freedom and create that illusion of progress with them. Because if you think about it, the user just placed an order. We know exactly what they ordered. We know where they want it shipped. We know all of that information because they just put that into the system, right? So we could just show that information to them once we've sent that off. It doesn't really matter that it hasn't actually been stored yet. We don't need to wait for that to be in the database before we can show it to the user, because we know it will get done at some point, right? You could even sort of keep that around in a local storage cache kind of thing. But of course, if we do that, we also know that at some point that data is just not going to be trustworthy anymore. And as we let go of synchronous communication, we lose that sort of flexibility to be able to say, this order needs to be stored within, half a minute or so, which we would have handled by a timeout. And we don't really have that anymore. So if we still want to be able to say, it can't take longer than 30 minutes to store an order, what do? And that's what brings me to SLAs, right? Because for each of those steps that we've identified in the process that we've now decoupled, we need to also think about, okay, what's an acceptable amount of time for this to happen, right? And what we then want to do is make that explicit and work with those. Now, when we find those relevant SLAs for each of those individual steps, or even combination of multiple steps, then how do we enforce those SLAs in a message-based system? And that brings me to future messages. Now, I find that future messages are an incredibly powerful feature of message-based systems, and it's still heavily underused. Now, the thing is, what you can basically do is send a message that is going to be delivered at some point in the future, right? This is supported by many messaging technologies out there, like Azure Service Bus, Amazon SQS, and RabbitMQ if you're using a specific plugin for that. And there are many middleware technologies that support this as well. Now, how does this then connect to those SLAs? Well, basically what we want to do is we want to calculate the SLA expiration time and then use that as the delivery time of our message. And then when that message comes in, we can go and verify whether that SLA was violated or not. And if that is the case, then we can take whatever appropriate action, like, for example, canceling the order at that point. Okay. Again, for this one, it's something that we need to accept once we move from synchronous to asynchronous type of communication, that there's going to have to be some changes to our user interface as well. So we want to adjust the language in the UI. We can use a little bit of creative freedom to create, the illusion of progress, but then we still need to be mindful of defining those service level agreements on the process level and enforce them with delayed messages. And that brings me to the next problem. Things occur out of order. One of my favorites. Who wouldn't love their sock drawer to look like that? I wish mine would look like that. It doesn't. But the thing is that when you start to think about it, we also need to ask ourselves, do I need it to look like that? Does it stop being functionable or operable if I just would, throw them all in a bin and I don't care where everything is? Let's consider our sort of order workflow, right? What we basically have here is we have a prerequisite hidden right there because I want to package the order after the order has been both stored and charged. What is my problem? That's happening in different services. And I don't really know when both of these things have happened, right? And I find that this is usually the reason that we seek order. It's not that we need the order, it's that we're trying to handle complex prerequisites. Now, what we could do is say, we're going to send out the messages in the order that we want them to be processed. And most of the time they will, until they don't. Because the thing is that we can't really guarantee that things that we send out a certain way are going to be processed that certain way. Because there are many, many reasons that could lead to your messages being processed out of order. Now, first one could be latency. One of the fallacies of distributed computing, right, is that the latency is 0. It's clearly not. But it could also be processing time. I'm sending out message A, and then I'm sending out message B, but it takes twice as time to process message A than it takes to process message B. Subsequent messages are going to appear out of order as well. It could also be concurrency, right? If we're scaling out a specific worker, then in-queue ordering, bye-bye. You don't have that anymore, especially if you're prefetching, for example. It could also be to do a sort of increase in the load, and there's only one specific service that is affected. There's a buildup of messages in that queue, and the rest of the system is keeping up. It could also be to retries, right? One of the great things of messaging is it's a lot more resilient, but what do? We retry, we do back-off mechanisms and things like that. Again, out of order. And it could also be service unavailability, actually. I should change that. It should be unavailability. Because if one of those services is down, the rest of the system, if they're autonomous, should be able to continue operating without too much friction. But it does mean that if the rest of the system keeps up, that you might see some messages being processed out of order. So one of the things that we could do is say, let's just make it ordered again. And what can we do? We'll just execute step 1 and wait until that has been successfully done, and then we'll send that message to kick off step 2. And so forth. That would work now because it doesn't matter how much latency there is, how many retries we do, or how long it takes, because we're just not kicking off the next step until we know that we can. But what have you done here? You've taken all of the benefits of messaging and then comfortably walked to the bin and thrown them in. Because the thing is, it's not that you've only made it slower. Another reason that we could sort of slow down these types of systems, right? We're just increasing the latency. But another problem is the coupling, right? Because the thing is that now the sales service is aware of payments, and payments is aware of shipments, and shipments is aware of invoices. And this is just a single flow. Imagine that you have 30 workflows in a system or more. Yeah, that's how you build that distributed ball of mud, one step at a time. Now, a common misconception as well is that people say, well, we're using messaging, so we're not really coupled together. Yes, you are. It's not because there's not a direct reference or you're not doing a direct API call that there's no coupling, right? You have command-driven type of communication here. So what can we do then? And that brings me to the orchestration pattern. Now, orchestration is basically going to introduce a central component that is going to drive the business process to completion. It's going to have all of the state about that process. And based on that state, it's going to make decisions about what is going to happen next and when it should happen and so forth. And it's basically a sort of mechanism that can help us recreate that order if we really, really need it. So let's see how that would look like if we would introduce an orchestrator. Now, we would have our user placing that order, and that is going to kick off the orchestrator. At that point, it's going to instruct both sales and payments to do their work. And then sales come back and says, yeah, got the order stored. And at that point, the order orchestrator will look at its prerequisites and say, I can't just package this just yet because I need it to be paid as well. But it can continue with updating the customer status, for example. And then when payments is ready and it says, yeah, I'm done, then it can continue with the rest of the flow and say, now I'm ready to start packaging and finish everything off, right? So this is a lot better because now the underlying services are not aware of each other anymore. They're not coupled to each other anymore. Now, clearly, we've just moved the coupling up, right, into the order orchestrator. But if they are workflow specific, then at least you've isolated that a little bit. But, and I want to stress this a lot, you need to be really mindful of the amount of coupling that you introduce in an orchestrator, not in an order orchestrator. Because the thing is that, these are also prone to becoming their own little monoliths because it's so easy to add and remove something there, right? So we could, very simply for this specific example, we could pull out, for example, everything regarding the stock and just keep that focused on the order fulfillment part. And then we can say, for the customer status, we don't need orchestration. We're just going to subscribe to the event and do whatever we need to do. And for the stock orchestrator, we're just going to subscribe to the order packaged event and do whatever we need to do in terms of, the stock. And that's completely independent now. And that really is going to narrow down the amount of coupled components. This is still too much. This is still just an example for you to sort of be able to visualize it. Now, the main reason that I would look out to use the orchestration pattern is basically to handle those complex prerequisites, or also to handle something like compensating transactions, right? Think of a scenario in which your customer wants to refund something. And now you need to generate a credit type of invoice. And now you need to be able to refund that part of the order that they sent back. If you look at the dependencies of that order orchestrator, it already knows all of the services that it needs to actually be able to do that, right? So it becomes really easy to do that. But it's also important to be aware that there are many downsides also with this. Why? Because we introduce a single point of friction. Now, every message that is basically coupled to that process needs to go through the order orchestrator because otherwise it's not a single point of truth anymore. And it can't sort of say like how the process needs to work. It needs to be the single point of truth and therefore a single point of friction. Also not always easy to scale these. And again, it's important to guard our coupling here. It's always a sort of trade-off exercise that we're going to have to do. Okay, to recap that part, expect out-of-order messages. At some point, they will happen. If you haven't thought about this before, and you're just, in a production environment and things have happened out of order, it can get really tricky. Because if you have something that fails, you're already lucky. It could just be side effects. It could be something that slumbers in the system as well and just has, ugly type of side effects like paying people too much money back or something like that. Test those out of order cases so that you get a sense of how your system would respond if that would happen. And consider how the orchestration pattern can basically help you manage those more complex workflows that you find in your system. And I haven't really talked about this yet. Of course, guarding the coupling, really important. I can't stress it enough. If you would be able to choose, then you would, if you have a truly autonomous service, you'd only ever have orchestration within that service. Because once you have orchestration across multiple services, you're coupling them together in that orchestrator again. But I haven't talked about choreography, which is the alternative if you don't want to use orchestration. That's the other pattern. But it would take me a full other hour to talk about that, so hopefully next year. But if you have any questions, I'm happy to chat about it, then come find me after the talk. That brings me to the next problem. It's impossible to troubleshoot failures, right? Another problem that affects any type of distributed system, really. Because the thing is that in a sort of monolithic architecture, and a sort of synchronous type of context, our code execution path looks something like this. We can just look at our call stack. We can just see how's the thing behaving, this code, that code, and there, and we have that call stack to basically guide us. But as we move to a message-based system and things are flowing from here to there, when we look at it from the code execution perspective, it looks somewhat like that. So it becomes a lot more complex to try to understand what is happening and in which order and where did this come from and what was the effect that caused this message to appear here, right? Now, the thing is that when we look at those individual services, they may be simple in isolation, but putting it all together becomes really complex. Now, luckily, again, there are ways to sort of deal with this and mitigate that a little bit. And the first one is testing, right? I can't stress it enough. Who attended Ian's talk earlier today? Not enough hands. Go and rewatch it on the stream. Because the thing is that if you build distributed complex systems, having a strong testing strategy is going to be really, really important for you. Because otherwise, how do you know that actually everything is working as you expect? But the thing with testing is you only really usually write tests for the scenarios that you're actually aware of. So there's always some blind gaps as well. And that's why we also need to invest into observability. Now, observability is basically a technique that can help us create visibility or bring back that visibility that we lost into a distributed system and basically recreate our call stack that we gave up. How are we going to do that? By collecting telemetry. That can be traces, logs, and metrics. And the most important project to do that right now is OpenTelemetry, right? Now, that's basically the industry-wide standard, and it's currently adopted by most, if not all, vendors. It's also available cross-platform and cross-runtime, I think 11 programming languages. And I could talk about this for a full hour, and I did. I did a talk about this actually at NDC Oslo, so if this is a challenge that you're running into, then yeah, scan the GitHub QR code. It will take you to one of my GitHub repositories where I have a recording available of that talk. And that brings me to our last problem. We did not expect duplicate messages. Now, the thing is that in a message-based system, every send or publish operation is by definition an at least once operation. If it's going to happen at least once, we also have a guarantee that at some point it will be more than once, right? Now, usually in a sort of business type of scenario, we don't want to have that sort of maybe once type of scenario. We want it at least once. But that also means that we need to be able to deal with duplicates. Or we need all of our handlers to be idempotent. Now, the thing with idempotency is I find that's one of the sort of, the biggest paradigms, really, in distributed systems. It's super easy to explain this with the example of a light switch, right? We have two types of light switches. One is a flip switch, and the other one is a push switch. The push switch is not idempotent, because if I push it multiple times, the state of the light is going to change every time I push it. The flip switch, I can flip the switch down as many times as I want. It's not going to change the state of the light, right? Translate that into idempotency in a system, and it's not easy for me to explain that to you anymore. So what do we do with difficult problems? We avoid them and we work around them, and that's why we have message deduplication. Now, that's basically a mechanism that helps us detect whether a message has been processed before, right? Again, that is supported by some brokers out of the box as well, like Azure Service Bus or Amazon SQS, and again, there are messaging middleware technologies that can help with that as well. Now, if we find that it's a duplicate, then it's fine, then we'll just throw it away. How does that work? It works based on a deterministic message ID. So we still need to make sure that when we send a message or when we publish an event, that the ID that we use for that is going to be deterministic, so that if we retry that operation, we're going to generate the same ID so that the broker can then deduplicate it for us. Okay? That's a little bit of a more manageable type of challenge. Now, it's also important to understand that this usually works based on a deduplication window, because what happens is that the broker or the middleware technology is going to basically keep track of all of the messages that were successfully processed, so that it can actually make a decision on whether it's seen that message before or not. In a very high throughput type of system, we can't keep those messages forever. So usually we'll keep them for a window of time, the deduplication window, and beyond that window, we'll just treat it as a unique one. Does that mean that we can completely forget about idempotency from here on out? Unfortunately, not. And that's basically because in a distributed system, we're now using different types of infrastructure. In these modern systems, we have document databases for this and relational databases for that, and we'll store some of that information in blob. And that's great because we're using the right type of storage mechanisms for the right type of reasons. But we don't have any distributed transactions anymore, right? Now, the thing is that when you look at all of those technologies in isolation, they do offer some kind of transaction management, right? Relational database, database transactions, document database like Cosmos, partition-based transactions. Even in Azure Service Bus, you have cross-entity transaction. But what is the big challenge? We cannot combine those transactional guarantees together, right? And because of that, we have that sort of multi-phase type of commit situation. So if you're, for example, in a scenario where you need to access different types of infrastructure, you are basically stuck. Now, one of the sort of typical patterns that we use in message-based type of systems to handle this type of scenario is the outbox pattern. Now, it's important to understand that this doesn't actually mimic a distributed transaction. It's just going to give you consistency across the database operation and a broker operation, but just a single database, not 15, right? So it's important to understand that if you have a scenario, for example, like, I want to generate an invoice for this order. And what I want to do is I want to store the actual PDF on blob storage, keep a reference to that, blob pointer in my document database or relational database, and I also want to send a message. That would not be covered by the outbox pattern. So how would you solve that type of problem? And that brings me to the Saga distributed transactions pattern. Now, this is basically a failure management pattern that is basically going to use a sequence of local transactions to be able to ensure that data consistency on a step-by-step basis. What we're basically going to do is send a message to store some information to this type of infrastructure, and if that succeeds, we'll send off the message for the next type of infrastructure, and then if something fails, we'll also roll back at the end. Now, to make this a little bit more visual for you, I've put this in a drawing, right? So if we have the Saga on one side and we want to store some information in SQL, we send that first message, we do that, that succeeded, awesome. Then we can continue, send off another message because we want to store something in Cosmos as well. Great. Now we're sending something else to another SQL database in another service, and that fails, right? What do we do then? Well, the Saga will take care of that. Go back to service A, undo what they did in Cosmos, and then send another message and undo what they did in SQL. This is a terrible example, and I did it on purpose. Because if you find yourself in a situation where you're trying to mimic a distributed transaction and accessing multiple services, you got your service boundaries wrong. Okay, so that's also something that you can sort of treat as a red flag, if you will. But it does still sort of explain how the pattern works in isolation. Okay, so to recap this last problem. When it comes to idempotency, I can't really give you a silver bullet, but I can give you multiple strategies, right? If you're starting from scratch and you can do it, make your changes idempotent. And this is going to be hard because it's going to take continuous effort. Whenever you change something, you'll have to think about, is this still idempotent? It requires everyone to be aware of this problem and to fully understand it. It's tricky, but it can be done. So if you have that option, then do it. If you need to mimic some kind of distributed transaction, then you can use the Saga distributed transactions pattern to sort of mimic that and make use of the individual transactional guarantees of all of the types of infrastructure that you use. If you have communication that needs to happen across components, and it's within your own system's boundaries, please do not do it over REST APIs because you're just making life harder for yourself. Do it over queues because then you can use that message deduplication feature out of the box as well. And finally, if you need to integrate with REST APIs that are out of your control, then you'll need to figure out, do they handle idempotency? And how do they handle idempotency? Usually that's not a magical thing. Again, there's going to be some kind of a deterministic ID so that the other side can figure out whether they've seen that request before, unless they are fully idempotent out of the box. And if they're not idempotent, yeah, that's a tricky situation, and you'll have no choice but to investigate how you deal with compensating requests, and that's in that type of scenario. And that brings me to the end of this session. Wow. Now, I know I threw a lot of information on you. There was a lot to digest in the session, so I'm going to try to summarize it a little bit. Now, I love working on message-based systems. I find that it's really fun. They're really powerful. But I would also say, like, only introduce that complexity if you actually need it. Who was in my talk yesterday? Okay, wow, quite a few hands. Well, welcome back. So yeah, you'll have an idea of why I'm saying this as well, is make sure that you actually need it if you introduce all of that complexity in your system. And one of the ways that I like to think of it is that messaging buys you options, right, to address things like scalability and reliability and reducing the coupling and handling those performance concerns. But you have to commit to decoupling your logic and data and to try to build those components to basically operate in an autonomous manner to become really successful. Think also about how out-of-order processing is going to affect your workflows, and try to build your system in a way that it doesn't really matter as much, right? Also invest in observability so that you understand what your system is actually doing in a production scenario, because there will always be, these side cases that we never thought about, and we're then trying to figure out what happened. So it's really important to be able to go to some kind of tooling and try to understand what your system was doing in that live environment. And finally, make idempotency a key pattern in your design. It's not something that you can forget about. This is going to be also really, really important. And if you take all of those things into the back of your mind, then it's going to be super fun. Cool, thanks a lot for listening. If you scan the QR code on the right, then that will take you to my GitHub repository. I have a bunch of additional resources for you there, lots of the patterns that I discussed. The QR code on the left will take you to our company website. If you need help with building message-based systems or you have questions, then you can also always reach out to us. Thanks a lot.